Welcome to your lesson 2.7 for Algebra 2. Today we're going to talk about absolute value functions and transformations. The parent function for absolute value functions is the function y equals absolute value of x. The graph of y equals absolute value of x is V-shaped and symmetric about the y-axis. So for every point xy on the graph, the point negative xy is also on the graph. So what you have is two rays starting at the vertex 0, 0. To the left of x equals 0, the graph is given by the line y equals negative x. And to the right of x equals 0, the graph is given by the line y equals x. Notice both of those, the two lines there have a slope of 1 or negative 1. They go through the points either xy on the right or negative xy on the left. The highest or lowest point on the graph of an absolute value function is called the vertex of the absolute value graph, and the vertex of the graph y equals absolute value of x is 0, 0, so it's our origin. Transformations of general graphs. For absolute value of a greater than 1, the graph is vertically stretched and y equals a times absolute value of x is narrower than the graph of y equals absolute value of x. For absolute value of x less than 1, so things like 1/3 or negative 2/5, the graph is vertically shrunk and y equals a times absolute value of x is wider than the graph of y equals absolute value of x. So for example 1, we're going to graph y equals 1/3 absolute value of x and b y equals negative 2 times absolute value of x, and we're going to compare each graph with the graph of y equals absolute value of x. So first thing we want to do is draw y equals absolute value of x, and that is this V-shaped graph that goes through 0, 0, and then to the right of 0, 0 is the line y equals x, and to the left it's this portion of the line of y equals negative x. So this upper V is y equals absolute value of x, and it's good to go ahead and draw that in so that you can make a good comparison of your new graph as compared to the parent function y equals absolute value of x. Okay, so the graph of 1/3 absolute value of x is the graph of y equals absolute value of x vertically shrunk by a factor of 1/3. Alright, so the graph has a vertex of 0, 0 and passes through 3, 1 and negative 3, 1. And you may be going, but well, how do you know that? Well, you could make a table of values. That's one thing that you can do. Another thing that you can do is go ahead and put your vertex at 0, 0. Notice that the value for a is 1/3. What you do is starting at 0, 0, you draw an array where it has a slope of 1/3. So you go up 1 from 0, 0 and to the right 3 from 0, 0, and that gives you that point 3, 1. And then you draw in the ray. And then you go back to 0, 0, and you use a slope of negative 1/3. So you go up 1 from 0, 0, and to the left 3, and then you draw in that ray. And that gives you your the graph of y equals 1/3 absolute value of x. The graph of y equals negative 2 times the absolute value of x. Before we approach that, we want to go ahead and draw in y equals absolute value of x. That's this upper V. That's our parent function. Now, for this one, it's going to be stretched by a factor of 2, but because of that negative, it's also going to be reflected across the x-axis. That's what that negative tells us. So the negative in front of the 2 tells us that we're going to have a downward opening absolute value function instead of an upward opening absolute value function. Okay, so you draw your vertex at 0, 0, but this time you're going to go down 2 and to the right 1. Okay, for our slope of negative 2 there. And then we're going to go left 1, and down 2, because rise over run, so the 2 is the rise part, and that will be the other part. Okay, so the negative in front tells us that it's going to be downward, and the 2 tells us how much to stretch by. So that means you're going to go because we're stretching by 2 means you're going to go down 2 and right 1. You're going to stretch it 2 vertically for every 1 unit you move horizontally. So it ends up going through the points 1, -2, and -1, -2. Okay, now we're going to move from having our vertex at 0, 0. We're going to graph functions of the form y equals a times the absolute value of x minus h plus k. So we're going to graph y equals -3. Okay, so far we know it's going to be reflected across the x-axis because of that negative. It's going to be stretched by 3. And then it's -3 times absolute value of x plus 2 minus 1. Compare the graph with the graph of y equals absolute value of x. Okay, if you'll notice, in the general form, we have x minus h inside the absolute value signs. That's going to be important here in just a second. And then we've got plus k. The first thing you do is you identify and plot the vertex. You've got to know where your starting point is. Okay, so if you look over here at our graph, we have our y equals absolute value of x. If you want to go ahead and draw in that upward facing v there, that's our parent function that will help us make our comparison. Now, to plot the vertex is at hk. Okay, so our general form is y equals a times the absolute value of x minus h plus k. So we need to identify what h and k are. So if you look over here in the little bubble to the side, it says to identify the vertex, rewrite the given function as y equals -3 times x minus -2. And that's because there's x minus h in the original formula. And then plus -1 because the original formula has plus k. So once you have it in that form where you have x minus something inside the absolute value bars and then plus something outside the absolute value bars, you can read what h is and what k is. So h is -2 and k is -1. So we know our vertex is at -2, -1. Now from there, we look and we go, okay, it's going to open downward, and we need to consider slopes related to 3. So we need to move down 3 units from our vertex. For each unit, we move to the right or the left. So the first point I would plot would be I would go down 3 from -2, -1, and then to the right 1. And that gets me to -1, -4. Then I go back to my vertex, and I go down 3, because I have a downward opening absolute value function, and I would go left 1. Okay, so from -2, -1, we go down 3 and left 1, and that gets us at -3, -4. Then we play connect the dots on either side, and we give ourselves our V-shaped graph. Okay, so you have to bring to it the knowledge of what you expect the absolute value function to look like. It's going to be V-shaped. Okay, you want to look at your value for A and decide whether it's going to be upward opening or downward opening. If you have a positive value for A, it's upward opening. If you have a negative value for A, it's downward opening. Then you want to find the vertex. You plot the vertex, and then you use whatever A is along with your knowledge of whether it opens down or up to plot 2 other points. And then you draw in your V-shaped graph. Now, compared with y equals absolute value of x, the graph of y equals -3, absolute value of x plus 2 minus 1 is the graph of y equals absolute value of x first stretched vertically by a factor of 3. So the stretching actually happens first, then reflected across the x-axis or in the x-axis, and finally translated left 2 units and down 1 unit. Okay, because if you look at -2, -1 compared to 0, 0, -2, -1, you've moved 2 units to the left and down 1 unit. Okay, so for example 3, we're going to come back and we're going to do that in video number 2.